Hey everyone! In this video we're going to be learning how to do hypothesis tests for population standard deviation. So this is going to be similar to our other hypothesis testing, but specifically we're going to be working with standard deviation. So the distribution we're going to use in this case is called chi-square. So the chi-square distribution has the following property. If a simple random sample of size n is obtained from a normally distributed population, so that's one of the key things. The population has to be normally distributed, so we'll check that. And we have the mean and the standard deviation. Then this is how you compute chi-square. So this is our Greek symbol chi, and then notice it's squared. That's why we call this chi-square. So we take the sample size, subtract 1, multiply that by the standard deviation of the sample squared, also called the variance of the sample, and then we divide that by the standard deviation of the population squared, also called the variance of the population. And so this has a chi-square distribution, and we also need what's called the degrees of freedom. So that's going to be our sample size minus 1, and then like I said, s squared, or our standard deviation squared, is from our sample. So some of the characteristics for our chi-square distribution: it is not symmetric like some of our other distributions. We'll see visually that it's skewed unless we have larger sample sizes. The shape of the chi-square distribution does depend on the degrees of freedom, similar to the student's t distribution. And then as the number of degrees of freedom increases, the chi-square distribution actually becomes more symmetrical. And then the values of chi-square are actually never going to be negative. So here's a visual for us. Notice if you only have 2 degrees of freedom, that's blue. This is extremely skewed. And then we start increasing the degrees of freedom. We have 5, that's the red one. And then as we go larger and larger, like 30 here with this purple, this looks much more symmetric. So increasing the degrees of freedom, which comes from the sample size, so increasing the sample size makes this more symmetric. But it's not symmetric with a lower degrees of freedom. So what we're going to do is we're going to test hypotheses about a population standard deviation. So let's walk through our testing of our hypotheses, our steps for that. So in order to test our hypotheses about our population standard deviation or variance, we can use the following steps, given that the following are also provided. So the sample has to be obtained using a simple random sampling. And also, like I said a little while ago, the population has to be normally distributed in order to use this. So here's our steps. Determine our hypotheses, our null hypothesis and our alternative hypothesis. And then know, like we've done previously, that we have 3 versions of our test. Two-tailed if we have a different than or not equal to, left-tailed if we're thinking of something less than, or right-tailed if we're interested in something greater than. And notice our symbols here. This is our standard deviation symbol, so that's what we're testing. And then after that, we're going to select our level of significance, alpha. Normally this is given to us in some regard, so we'll have that. And then step 3 for the classical approach. So we'll have a different step for the p-value approach. For the classical approach, we're going to compute the test statistic. So notice the difference in the notation. We have a little subscript 0, so this is chi-square naught, or sub-0, and that just denotes our test statistic. So we'll compute that using this formula. And then we're going to be using our chi-square distribution table, and we have to know the sample size to get the degrees of freedom, and that will give us our critical value. Okay, so here's a visual for our conclusions that we'll make on the next step actually. So if we have a two-tailed test, we're interested if our test statistic is in one of the critical regions. And remember I said that chi-square distribution, it's not negative, so it's just going to be that there's a smaller positive value. We're wondering if our test statistic is less than that critical value or greater than the larger critical value. Left-tailed test, we are just interested in our test statistic being less than the critical value, and then right-tailed test if our test statistic is greater than our critical value. So here's the same thing, just sort of written out. Two-tailed test, we're talking about our test statistic less than or greater than one of the 2 critical values. Left-tailed is strictly less than, or right-tailed is greater than. In each of these cases, if that's true, then we reject our null hypothesis. And then we state our conclusion. So then the p-value approach, we actually do the same step 3. We compute our test statistic chi-square. Then we go to our chi-square distribution table and we find the p-value based on our degrees of freedom. So we'll work through all of these. And then if we are doing a two-tailed test, our p-value is actually going to be twice the probability from our table. So just keep that in mind if it's a two-tailed test. And then here's our left and our right-tailed test. So with p-value, we're basically trying to see if that probability or p-value is less than our chi-square or greater than our chi-square for right-tailed. And then we can also use technology, which I'll show you that as well. And then if our p-value is less than our level of significance alpha, we reject the null hypothesis. All right, so just another reminder, we do need to have our populations normally distributed in order to use these processes with our chi-square distribution for the standard deviation and variance. Okay, so let's take a look at this example. The quality control engineer for M&Ms tested whether the mean weight of fun-sized Snickers was 20.1 grams. We did this in a previous video, but we were talking about the means last time. This time we're going to be talking about the standard deviations. That's why we're going to use chi-square. So suppose that the standard deviation of the weight of the candy was 0.75 grams before a machine recalibration. The engineer wants to know if the recalibration resulted in a more consistent weight. So basically they have the machine that produces these candies, and there was a variance. There was a standard deviation that any candy could be off from the 20.1 grams plus or minus 0.75. So they want to recalibrate that machine and make it more accurate. So we're going to conduct the appropriate test at the 0.05 level of significance. So here's the data from, if you count, 11 different samples from the candy, and so these are the weights in grams. Notice they are not all 20.1, so they do vary quite a bit. So we want to know if the recalibration made this more consistent. If the 0.75 is still how much the candies vary in weight, or if it's less. Okay, so we're going to use a normal probability plot to go ahead and verify that we can use these procedures. So let's do that real quick. Okay, so what I have here is StatCrunch, and what we have is just the data values from our sample. So I just inputted those 11 values, and I'm going to just check that the sample is normally distributed. So I'm going to do two things. I'm going to do a QQ plot. So for this one, I'm just going to select the column, and I'll go ahead and check a few things. I want to just know the correlation statistic. I don't necessarily need that. I can tell visually, but I'll talk about that. And then we'll click on normal quantiles on the y-axis. I'm also going to include some horizontal lines, and I'll hit compute. Okay, so here's our normal probability plot, and basically what I'm looking for is if the data is symmetric about the 0 here, which it is. There's about half the points above and half below, but also if they follow this line, like if they are linear in nature, linear enough, and they are. So far this looks great. The correlation coefficient of 0.97, we can double check that with our critical value that we've learned in the past. So I'm going to go to that table real quick. And so this tells me the critical value based on my sample size. So for size 11 right here, the critical value is 0.923. And so our correlation coefficient that was calculated on our normal probability plot, if you remember a moment ago, is 0.97. So as long as that's more than this critical value, then it's basically saying it's linear enough. And so that looks pretty normal. So then also what we do want to check is that there's no outliers. You can kind of tell that there's nothing in this data is too far off from the other values. But visually, if you'd like to see it, we can do a box plot. And so we would just do our column, and I'll go ahead and draw the boxes horizontally. And what I'm looking for is any outliers. Outliers would be if there was dots on the side of this, like they're too far off. So I'll show you really quick what an outlier would look like. Let's just put in something random here, and I'll recompute this and take a look. Yeah, so there's clearly an outlier over there. And so this data without that random number, there was no outliers. So this is normally distributed with no outliers. So we're good to go. All right, so now let's talk about our hypotheses. So our null hypothesis is that the standard deviation is what it was, 0.75, versus our alternative hypothesis, which is our standard deviation is less than that. It's less than a left-held test because we're hoping that the machine calibration made the standard deviation decrease, making it more accurate to produce these candies. So this is a left-held test, and our level of significance was given 0.05. And we're going to start with the classical approach. So by hand, we can compute chi-square, our test statistic, and we have our degrees of freedom, which is 10 because our sample size was 11. Our standard deviation squared, or also our variance, you can compute that using software or calculator. And then our standard deviation from our population was 0.75, that was given, so that variance is that number squared. And we compute that and we get 7.291 for our test statistic. Let me just go ahead and show you that we can get our sample standard deviation really quickly. Okay, so just as before, I had my data in StatCrunch, so I'm just going to go ahead and say summary stats, columns, and I can do my standard deviation, but I can also do my variance. Okay, because I actually need the number squared anyway. So the number 0.6404, if we round, is where we got that from. If you square it, you're going to get 0.4101 if you round that. Okay, so then left-held test are based on our critical value, and we're going to go to our table to get this 3.940 value. So left-held, we're going to go ahead and say 1 minus our alpha because our table tells us anything to the right, so I'll show you what I'm talking about in just a moment. But keep that in mind, the left-held test, we have to say 1 minus this level of significance. So let me show you the table where 3.94 came from. Okay, so here is our chi-square distribution table, and so this is where we're going to get our value from. So we're going to look at our column for our degrees of freedom right here. We need 10, and then what we want also is, notice it says area to the right of the critical value, and so we are doing left-held test. So if we have a level of significance 0.05, then we have to say 1 minus that to get the area to the left. So 1 minus 0.05 would be 0.095. So that's this column. So we basically match up this column with this row, and so we have 0.095. And if you look at the left, we're in the 10 row, that would give us 3.940. So that's our critical value. Okay, so with our classical approach, our two numbers that we need are our critical value, which we just found from our table, which was 3.94, and our test statistic, which we computed a little while ago by hand. It was 7.291. And remember, if we have our test statistic in our critical region, that's when we reject the null hypothesis. So you can kind of already see we're not going to reject the null. We're not in the critical region for the left-held test. And so it's because our test statistic 7.291 is bigger or greater than, in this case, for the left-held test, our critical value, 3.94. So the quality control engineer does not reject the null hypothesis. Okay, so we're going to do this again. This time we're going to use the p-value approach by hand, and then I'll show you how to use technology to do the p-value approach. So same step 3, computing our test statistic is 7.291, and then remembering that we are doing a left-held test, we have our p-value based on our degrees of freedom, which is 10, and so it's going to be that the probability is less than this test statistic with 10 degrees of freedom. So then we would go back to our chi-square distribution table to finish using the p-value approach, and we would go to our 10 row for the degrees of freedom. We have our test statistic at 7.291, and we would end up with the value 3.94 again. How we would get that number using the p-value approach is we would keep in mind that the p-value is the area under the curve, and we are doing a left-held test. So even though we're looking for area 0.05, because we're looking to the left, we have to say 1 minus that to use the table. So same as we saw earlier, we would go to the 0.95 column in the table, and then that would give us that area to the right. So that would be like this beige color would be 0.95 as area. And that would give us area to the left is 0.05. And so because our test statistic is larger than the critical value associated with that area, then we're actually not going to reject the null. Our p-value is not less than this. So we same results or conclusion we got with our classical approach. And then I'll show you how to use technology to also verify that we would not reject the null hypothesis and actually compute the p-value. So the table gives us an approximate p-value, but we'll get the actual p-value using technology. All right, so now I'm going to show you how to do your hypothesis testing with, not by hand. You're going to just use technology here. We're going to use StatCrunch. And what you're going to do is you're going to go to, in this particular case, variance stats. So you do different options here depending on what you're testing. So for example, Z stats and T stats are for different means. Proportion stats is obviously for proportions. Variance stats is when you're working with standard deviations. So just keep in mind that variance is a standard deviation squared. So you're going to need to square your numbers here. Okay, so we are working with one sample because I only have the single sample in column 1, and I have data in column 1. So I'm going to say with data. And then what I'm going to do here is I'm going to select my column with the data. And now this is what I was saying. Notice the symbol. It's very subtle, but the symbol is your variance symbol. It is your standard deviation squared. So you need to go ahead and compute the square of that. So you're going to say our 0.75, which was our given population standard deviation. We need the variance. So we're going to square that number. That's what we're working with in order to use this software. Okay, so that was 0.5625. 0.5625. Also make sure that your test is the one you're working on, which in this case is a left-tailed test. Okay, so we are doing a left-tailed test, so change that symbol. And then also, one more thing to check, your critical value. So ours was 0.05, or level of significance. So put that in there, and then go ahead and just hit compute. And here we go. So notice what you have. You have your test statistic. So we had been doing this by hand, but there's your test statistic, 7.291, or 01 in this case, which might be more accurate than what we got by hand. Also, here's our critical value, which we had gotten from the table, so we can get this using technology. And then here is the actual p-value. Okay, so we were just getting estimates using the table, but here's the actual p-value. So it's 0.3. And in this case, if you actually know the p-value, then you just compare it to alpha. So if your p-value is less than alpha, you reject. Our p-value is much bigger than alpha. Remember, our alpha is 0.05. So this is not less, so we do not reject. Okay, so final conclusion. There is not significant evidence at the 0.05 level of significance to conclude that the standard deviation of the weight of fun-sized Snickers is less than 0.05 grams. So what that means is the recalibration of the machine, it didn't make more consistent weights for the candy based on our testing. And we did it 2 different ways, classical and p-value approach, and then we used technology to get more accurate with our p-values. All right, so this is how you do hypothesis testing about population standard deviation. Thanks for watching.